and then undo this. All right, I'm going to show you how to minimize this. There is some kind of an interesting mathematics in there, but it's not really within a subject within group theory, right? How do you minimize this? Well, basically, each CI, right, each of these numbers is actually a complex number with a real and an imaginary. I mean, it just depends on two parameters, right? Each CI is a complex number depending on two real parameters. Okay, so this is kind of a convention. Some people just use prime for the real part and double prime for the imaginary part. A lot of people use this convention, so that's why I'm using it in here, but it's not really that important, right? So in any case, so we have some kind of an expression that depends on these D complex parameters, so therefore there are two D real parameters. So we have to minimize this with respect to D. So what you need to do is to take the derivative of that expression, right? It's the CHC divided by CSC, and set it to be equal to 0. And do the same thing for the other parameters as well. So let me not repeat this, right? So that's, therefore you have to use, like, there are 2D equations in here, okay, that you need to solve. All right, that's one way, all right? Let me do it like this. That's one way that you can do. The other one is the, you can actually set up the problem as a Lagrange multiplier problem, right? Lagrange multiplier method. So the important point in here is that there's kind of a scaling. So you can set this to be equal to 1, for example, and which is basically the normalization. So as a result, your job is to minimize basically CHC subject to the constraint that the normalization is equal to 1, okay? So that's the problem in here. And people do this with the Lagrange multiplier method. So as a result, they define a function like this, minus lambda times the constraint. Lambda is the Lagrange multiplier. And then they take the derivative of this expression and set it to be equal to 0. And then find the value of the Lagrange multiplier by using the constraint relationship and so on, okay? But in any case, in both cases, we need to take derivative with respect to the real and the imaginary parts, right? I think I'm going to follow this, but at the end, we're going to reach to the same conclusion, all right? Okay, so here is the interesting part, okay? I can think of, I mean, these set of equations to be basically the equations with respect to the complex part of the derivative of this thing with respect to the complex parameter and its complex conjugate, okay? So let's say it like this. The equations are equivalent, okay? So you can do the same thing for the Lagrange multiplier approach as well. So let me magnify this a little bit, all right? But I'm not going to write down the equations for that case, right? Only in that case. So instead of taking derivatives with respect to the real part and the imaginary part of each complex number, I can think of the complex number and its complex conjugate as independent, right? So treat Ci and Ci star as independent, and well, take these derivatives. we know that they are not independent derivatives, right? What is important is that, well, they are not independent, but I'm just going to treat it like this. So when I take the derivative with respect to CI, any expression that contains the complex conjugate of CI star, I'm going to take this to be equal to 0, right? So only if the expression contains the complex number itself, I'm going to compute the derivative. But if, I mean, this is basically what we mean by independence. So the derivative of a complex number with respect to its complex conjugate would be taken as 0, right? If you make this assumption, then these two equations are equivalent to that equation, these two equations, right? And mathematically, these are simpler because all of the expressions are written in terms of the complex number and their complex conjugates. Okay. Why this is the case, you can actually show it like this. So, for example, the derivative with respect to the real part, you can think of it as, I'm just going to use this, sorry about this. I mean, you can think of it as a change of variable. So as a result, you have, when you express the derivative with respect to the real part in terms of these two derivatives, you basically get this, so that you can think of this as like the sum of these two derivatives, and the derivative with respect to the imaginary part is, I think I'm going to do the same thing, but I'm just going to eliminate these. So at the end, this is basically I times d over dci minus d over dci star. Okay. So in any case, as a result, if you have an equation where this derivative and that derivative of a function is 0, then this is the same thing as like for the same function, this derivative and that derivative being equal to 0, right? You can show that this is the case. Yeah, it doesn't matter what that constant is. When you take the derivatives, they don't make a difference. But yeah, some people write it down like that. Okay, but no problem with me. At the end, to compute what the lambda is, you need to use the constraint. So that's also important, but that part's not going to make any difference. Okay. Another thing in here is this, let's say, if f is, or the E bar is, yeah, f is a real valued function. Function of Ci star, then the derivative of f with respect to Ci star, let's say, is equal to the derivative of with respect to Ci complex conjugate. Okay. Which means, I mean, in this situation, if this is equal to 0, then it automatically implies that the other one is also equal to 0. So as a result, you only need to look at only one derivative. Okay. So as a result, I mean, this is kind of easier. So you just need to take a derivative with respect to this complex parameter. You don't have to look at the other derivative. So in that case, you get some kind of a complex equation, which somehow contains both of these equations, right? So that means, so this is minimize E bar. So that's basically this thing in here. Sorry, CSC.
Hocam biraz yukarı çıkarır mısınız?
Nasıl?
Bu şekilde. Teşekkür ederim.
So to minimize this, just let's say, yeah, let me write to minimize, all right? To minimize this, you basically solve this set of equations. So the derivative of this thing with respect to the complex conjugate of E bar being equal to 0, for I being equal to 1, 2, and B, right? All right, so as a result, this is a very simple procedure. How do we do this? Well, this is quite simple. Like, I mean, again, let's remember that this equation implies that the derivative of E bar with respect to Ci themselves are also equal to 0, which also implies that the derivative of E bar with respect to the real and imaginary parts of these parameters are equal to 0. Okay. So a lot of people, when they are doing minimization with respect to a complex parameter, they just write this thing down immediately without explaining why this is the case. Well, I don't know. If you haven't seen this up to that point, the real explanation why this is the case, well, this was the explanation. But otherwise, we don't do this these kind of steps usually. We just solve these, right? Okay. So the next thing is this. So this is CHC. That's actually a summation over CI star HIJ CJ, right? So if I take the derivative of this thing with respect to CI star, so there's a summation over I and J in here. So this time, I mean, expression depends on CI star linearly. So as a result, the summation over I disappears, and I basically have this Hij Cj, or you can think of it as like the matrix H applied on matrix C, and we are looking at the ith component. Okay, and I can repeat the same thing for the S matrix as well. So as a result, I'm just going to do this, right? So the derivative of E bar with respect to Ci star. So that's equal to, first of all, the derivative of the numerator with respect to Ci star. And then minus, I have the numerator divided by the square of the denominator and the derivative of the denominator. Okay, so this is the derivative of the denominator, this is the derivative of the numerator. That's equal to 0. So that's the equation. So the derivative of the numerator is H applied, the matrix H applied on Ci divided by this one. This one is, well, there's some kind of a number in here. CSC squared. So there's a square in here. And then S applied on C. And I'm looking at the ith component in here. What we do is I just multiply the equation by this expression so that this square just disappears. And I just call this number as lambda. So as a result, the equation basically reduces HCI minus lambda SCI equal to 0. Or you can think of it like this: HCI is equal to lambda SCI. All right, well, whatever. I mean, this is basically the generalized eigenvalue equation. We have met that equation in the case of the vibrational spectra. In that case, we had the mass matrix in here and a spring constant matrix in here, right? Or vice versa. I don't remember which one. Yeah, the mass matrix was in here. So it's a similar kind of a thing, right? But there are some special procedures for this. So I'm multiplying the Hamiltonian matrix with this column matrix, and the result is an eigenvalue times this S matrix, the overlap matrix multiplied, C. Okay, so here H and S are Hermitian. And because of that, you can show that all of these lambda are real and whatever. Okay. To convert this problem to an ordinary eigenvalue equation, this is what we do. So I know that S is positive semi-definite. So positive definite invertible matrix. Positive definite means it has positive expectation values. I think I have talked about this before, but I don't want to repeat the same arguments in here. So we can define the square root, s to the power 1/2, square root of that matrix. There is a procedure how we can compute this, but in any case, it can be done. It has an inverse, so there is an inverse also of square root, because it's invertible and whatever. So what I do is I basically multiply this equation by the inverse of the square root. So let me first write this thing down like that, okay? So the equation is this in that case. Yeah, let me write it down like that, right? And I'm going to simplify step by step. So first, this part in here. So this basically the square root of s applied on c. So as a result, let me erase the details in here and then just write this thing down as the square root of s multiplied with c. Okay. The second one is on the right-hand side. I have c in here, but I would like to write this thing down as a square root of s applied on c. So as a result, I just insert an inverse of the square root in here. Okay. And then I call this matrix as H prime. I call this matrix as C prime, in which case I get the ordinary eigenvalue equation in here. So H prime C prime is equal to lambda C prime. Is the ordinary eigenvalue equation. Here H prime is this matrix. This is the problem with the overlap matrix in here. If it is not identity, then you have to do this calculation in here. Whatever. This is Hermitian. So as a result, you can then convert this problem into this problem in here, where you still have to find the eigenvalues of that problem. But in any case, if you know MATLAB, for example, MATLAB is like matrix laboratory or something like that. There are procedures. I mean, there are functions in there where you just, when you insert in the matrix, it gives us the eigenvalues and the corresponding eigenvectors. There's also a function in there that directly solves the generalized eigenvalue equation, right? So when I'm trying to solve this equation, I don't do this trick. I just solve this directly in MATLAB. I just insert in both of these matrices and then it just gives me all of the eigenvalues, okay? So as a result, it's not really difficult in here, but in any case, by a trick, I can make this to be identity. If I'm doing this theoretical analysis in here, I can make it identity. Or in some cases, I just assume that this is identity. All right, so as a result, I don't have to do any of these things in that case, okay? Whatever you want, it doesn't matter. So let's say it like this. In simple theoretical discussions, we simply take S, right? This is the overlap matrix, to be identity. Okay, you just choose S to be equal to identity, which implies, I mean, Sij is the matrix elements are the Kronecker delta, so that's phi I, phi j. This implies that this is the same thing as saying that the set of molecular orbitals that you have chosen is an orthonormal set. Right? In reality, they are approximately orthonormal most of the time. they are approximately orthonormal. Not exactly, but in any case, in theoretical discussions, the mathematics is complicated, but this complication is irrelevant. So as a result, we just assume that this overlap matrix is identical. Okay, so you can think of it as an additional approximation to all of these approximations that we have made. Okay, I don't know if you have any questions in here. In the Lagrange multiplier situation, in this derivation, I just call this coefficient as lambda. In the Lagrange multiplier, the lambda just comes in directly, right? So as a result, you get the same equation again. Okay, and then there's this part in the representation. Of the symmetric group G. Okay, so let's just remember this. So R is an element of the symmetric group. We have the rotation operator. Let's remember what the rotation operator is. Applied on, let's say that a rotation operator applied on a wave function gives you the rotated wave function, and then we said that the value of the rotated wave function at a position R is the same thing as the old wave function at the inverse rotated position, right? This was the definition, if you remember, and then we have argued why this has to be so, right? And then from here, we just deduced that this has to be unitary because it's norm preserving and things like that. Just keep this in mind, okay? So let's say it like this. We require that d of R applied on each of these atomic orbitals is a linear combination of phi 1 to phi d, okay? This is how we have chosen, all right? So as a result, this is something given. So as a result, let's say that we have, let's just write this explicitly. So let's say that the rotation operator applied on phi I, when this wave function is rotated by R, I get the linear combination is this. I'm just going to write this thing down like that. So J is a sum from 1 to D. It's a sum over J. I'm going to call the matrices as AJI of R, phi J. Okay. There is a wave function. All of these are functions, but I don't want to write this thing down because it makes the equation complicated. Which means you can show that this is the case. A of R is a D by D matrix representation of the rotation R. So A is a D-dimensional representation of the group G. We don't have a representation of the group O3. I mean, G is a subgroup of that O3, but O3 does not have any, does not have this property in here. So it's only the rotations within the symmetric group has this property, right? Because of that, we basically have the representation of the symmetric group only, okay? Okay, the second thing is this, so let's see it like this. I'm talking about this approximate wave function, which is just a linear combination of all of these. Okay. All right, so consider the rotation operator. So that's basically sum of Ci phi I, all right? Consider the rotation operator applied to this approximate Hamiltonian, approximate wave function, sorry. So as a result, this is going to be sum of I, dr applied on phi I. So therefore, there's a double summation in here. So that's Ci. There's an Aj of R, phi j. So I would like to write this thing down as a sum over j, where there's a coefficient in here. And the coefficient appears to be the matrix AR applied on these coefficients, the jth entry. Okay. So as a result, I'm just going to call this as like Cj prime phi j. Okay. But Cj prime is basically is these coefficients. So as a result, the operation is basically converts the linear combination coefficients to a new set of coefficients where these representation matrices are the ones that does the transform. All right, I think this is quite simple, but I mean, how does the representation appear in different vector spaces? That's actually quite different. In the big Hilbert space of wave functions, you're basically converting a function into some other one by some kind of a rotation of the argument. Here, on this d-dimensional small vector space, you are doing this by some kind of a linear transformation on the coefficients, right? You can think of it like this. All right. In any case, so this is the approximate wave function. Sorry, it's just a linear combination. Let's just say some of the things. We can. I'm just going to make this symmetry statement. So this is the rotated wave function applied on this. So the coefficients are different now. It's a different wave function, so therefore the coefficients are different. Okay. What I know in here is that first of all, dr is unitary, so therefore the norm of the wave function doesn't change under rotations. I know that. Forget about the square, right? Because dr is unitary, which therefore implies that, if you remember, I used the overlap matrix to express the norm. So this basically says that C and C prime have the same norm. Okay, which means I can express it like this. This is like C times A dagger R as A of RC. So that's CSC, which then implies that this A dagger R S A of R is equal to S. So the S matrix doesn't change under this transformation. Okay, so the symmetry implies this. Okay, so that's one of the implications. The second implication is that the Hamiltonian is also has the symmetry. So therefore, the expectation value of the Hamiltonian in that approximate wave function and the rotated wave function, yeah, these are the same, right? I think I'm going to do it like that, right? So this is dr psi f hf. Right. Expectation value of my Hamiltonian in this approximate wave function or its rotated wave function should be the same. This basically is a statement about the symmetry of that effective Hamiltonian. In any case, this implies that in terms of matrices, we have this statement that the matrix Hamiltonian has the same expectation value in C and C prime. This is the same statement as saying that A dagger R H A of R is equal to H. Okay, I mean, the symmetry statement, I have to express the symmetry statement in terms of both the overlap matrix and the Hamiltonian matrix, right? And this is how I can do this. All right? I don't know if you have any questions in here. Just show that these two, I mean, if you remember, I have defined something called H prime matrix beforehand, right? This was that matrix. Just show that H prime basically commutes with AR. All right? Just show it. Is it? Yeah, I don't know. I'm not going to show this thing, but I'm just going to argue with this, all right? So I'm just going to make this approximation, sorry. So, right, if S is equal to identity, in that case, the first statement says A dagger R, A of R is equal to identity, which means A is a unitary representation of the group, the symmetric group G. The second one is this. This is the second statement. So that statement in here. So let's say it like this. This is A dagger H, A of R is equal to H. This implies that H commutes with A of R. Okay, so that I can directly apply the Schur's lemmas and things like that to that. Okay, so that's basically my symmetry statement. So this is the symmetry statement. In applications, I don't have to do anything like this. I don't have to repeat all the calculations until that step, right? What I need to do is, I first need to compute the representation matrices. This has nothing to do with the Hamiltonian. And the next, I know that this representation matrices has to be unitary. It's kind of given. And it commutes with the Hamiltonian matrix. Okay, so example. This is not quite the ammonia molecule, because in the case of ammonia molecule, I think the minimum number of atomic orbitals that we need to use is 7. I'm just going to consider an imaginary molecule. So let's say molecule X3, right? Where an s orbital from each atom is selected for a linear combination of atomic orbitals. Okay, so I'm considering some kind of a molecule with 3 atoms, 3 identical atoms, like, for example, ozone, right? Ozone is just an example. But however, I'm just going to choose orbitals. I'm going to call them as like, I mean, each one of them is an s orbital. Might be a 1s, 2s, doesn't matter. But I'm just going to call them as phi1, phi2, and phi3. All right? So that's the example that I'm going to choose. So let's say it like this. Phi I of R is basically defined as some kind of an, I don't know, the ns wave function of an atom, right? But I'm just going to take this as the s wave function of the atom I. So Ri is the position of ith atom, and phi I is the ns orbital of ith atom. Okay, in all of these situations, I is just a number 1, 2, 3. Okay, again, I'm going to assume that the overlap matrix is equal to identity. So therefore, this phi I, phi j inner product is equal to delta ij. In reality, it is not. So especially for 1s orbital, I know that the 1s orbital is non-zero everywhere, and it's always positive. So the overlap of two 1s orbitals is always non-zero. But this is an approximation, actually, right? So we are approximating it with then with this Kronecker delta, because I'm kind of assuming that the overlap of two 1s wave functions is almost zero. It's very small. So that's an approximation. I have the H matrix in here. So H matrix. So what is it? Well, I need to compute it like that. Okay. But in this H matrix, there's some kind of a molecular Hamiltonian involved. There's this kinetic energy term, Laplacian in here, and whatever, some kind of potential as well. And I don't know how to compute this. I'm just going to say something about this matrix in here. What can we say about this matrix? Okay. So in any case, so H is a 3 by 3 matrix, right? So there's some kind of a matrix like that. Now, because of the symmetry, some of these matrix elements are related to each other, and I would like to see how they are related, right? And in that case, I'm just going to solve the problem like this. Sorry, I'm going to look at the representation. Symmetry group. Sorry about this symmetry group. Right, this is C3V, but yeah, let's just call this as C3V, right? It's basically the isomorphic to the groups that we already know about this, right? Whatever the group is, I think I'm going to use this notation in here. So for the case of ammonia, that's the correct one. So although they are isomorphic, they actually differ in terms of the which operators, which kind of reflections and things like that are involved in there, right? So they are only differ by that respect. So as a result, we may want to use this convention from now on. In any case, that's the symmetric group. What's the representation? All right. So I'm just going to think about it like this. So this is this molecule. Yeah, I don't know how to draw the molecule. So that's the molecule in here. And I have these two, this 1s orbital in here. So let me call this as phi 1. And let me just consider this rotation in here. So R is this rotation. So let's say that R is counterclockwise rotation by 120 degrees, right? In that case, sorry about that. Let's see. In that case, the rotation operator applied on this orbital is going to give me the orbital in the second atom in here, right? Let me draw this as well. Okay, so that rotation will carry my orbital phi 1 into phi 2. Okay, so what happens is that the representation matrix A of R does the same thing with the column vectors. Right, I'm just going to show it like that. So that means A of R, therefore, applied on this column vector 1, 0, 0, gives me the column vector for this phi 2, which is 0, 1, 0. All right? So geometrically, you know how the rotation carries this orbital to some other orbital. So you have some kind of an idea about this. You express this geometrical operation in terms of these matrices in here. All right, that's basically what we do. All right, so therefore, I mean, you can easily see that, for example, this A of R um, basically converts the first standard basis vector to the second standard basis vector, which means that the first column is this column. Right, this is basically converts phi1 into phi2. That's basically what it is. Then I can fill out the rest in here. So this is just a permutation. It basically carries phi2 into phi3, in which case this second column is this one, and phi3 into phi1, so therefore the third column is this. All right? It's basically a permutation. Actually, in this case, since we are using the s orbitals, after rotations, the orbitals shapes do not change. And so as a result, all of these A of R matrices are basically just permutations. All right? In that case, you can, I mean, you don't need to write down the matrices, but somehow you need to be able to see how to compute the trace. That's the important part in here. And so, I mean, because we would like to basically find the invariant subspaces, all right? This is what we do in group theory, right? And for this reason, you need the tracing here, okay? So let me quickly do this in that case, okay? So think about this operation. Let's say this is a reflection like that. So let me call this as sigma, for example. It's just a reflection, right? So in that case, let me show the orbitals like that. So this is the phi1 orbital, phi2 orbital, and this is phi3 orbital. So you can see that the sigma reflection, basically the changes phi1 into phi2 and phi2 into phi1, but basically converts phi3 into itself. Phi3 is left invariant. So therefore, the matrix for sigma, the representation matrix for sigma would basically leave the third vector invariant, and they convert the first two vectors into each other, right? And so as a result, you can see that the trace is equal to 1. Okay, so let's quickly do this. So we have the identity in here, the sigmas and sigma prime, sigma double prime, and we have r squared in here. It's the same group, except that the names change. And the representations are U1, U2, and U3. This is the trivial representation. The dimensions are 1, 1, 2. This has -1, 1 in here, and this has 0, -1, right? This is the character table for that group. What are the characters of my representation? Well, identity has a trace 3. Reflections have a trace 1. The rotations have 0 trace, which means, yeah, you can easily see by inspection that the sum of the first and the last rows gives us the characters in here. So therefore, the A is a direct sum of U1 plus U3. Okay, which means H has a non-degenerate and doubly degenerate eigenvalue. Okay, so somehow there are 3 energy levels. One of them is basically one of these energy levels correspond to a wave function that transforms like U1. This is quite easy to find actually. So it has some kind of an energy level in here. And then there are these 2 energy levels that transform like U3. They have to be degenerate. We have seen why this is the case. Okay, by just looking at the representation and the composition of the representation, I can see that there is actually a doubly degenerate level in the Hamiltonian of that problem. I don't know if it is the ground state or the excited state. I don't know. That depends. That depends on the physical system. In some cases, just inverted. In some cases, this is like that, right? I don't know that, but I know that at least two of the levels have this degeneracy in here. This without actually even writing down what the Hamiltonian might be. Okay, so that's the interesting part in here. I think we can continue with this on Wednesday, but in there, I'm just going to show that the Hamiltonian is of that form. So there are these diagonal entries. So let me kind of show it like that. This is the basically the expectation value of the energy in each of these atomic orbitals. So they have to be equal to each other. And then there are these coupling between these different orbitals. But since they are all neighbor to each other, that the coupling is basically has to be the same. So you can easily show that what this thing is, what the energies are. Let's just compute this on Wednesday, right? So, but let me stop in here.